In this tutorial, I'm going to review the mini unit we did at the beginning of the year called The Nature of Science. In that unit, we talked about the parts of an experiment and how those different parts of an experiment come together to create a valid test or a fair test of whatever your question is. In science, you usually start with a question that you're trying to answer, and then you make a prediction, usually in the form of a hypothesis. So we're going to start with this experiment that I have here, a very famous experiment by a guy named Louis Pasteur. And this experiment basically is about what you need to do to protect food from going bad or getting bacteria and other things growing in it. So in this experiment, he's testing the hypothesis that food spoils more readily or more easily if it is left open to the air. Louis Pasteur hypothesized, he was one of the first people to hypothesize, that whatever it was that made food spoil might actually be floating in the air. So what we have here are two setups, two different trials of the same experiment. On top, we're heating some broth in a flask, letting it cool, and leaving the top open to the air. And then we're waiting to see if anything grows in our broth after just letting it sit out for a week or so. In the bottom trial, we're doing the exact same thing. We're heating our broth, we're letting it cool, but then we're going to cover it with a stopper. And then we're going to wait and see what happens. So in this experiment, you can see that waiting on top produced growth inside of the flask, and waiting on the bottom produced no growth until the flask was opened at a later time, seemingly proving that the hypothesis has merit, showing that, it's supporting the hypothesis, right? The idea that leaving things open to the air encourages some kind of contamination or growth. So what are the parts of this experiment? Okay, take a second, pause the tutorial, and see if you can fill in the parts of this experiment on your own, and then come back and see how I did it. Okay, so the hypothesis here, we said already, was that leaving something open to the air will lead to more spoilage. So open food spoils faster. The rationale for that is the explanation of why we think it, right? So what was his thinking? His thinking was that there's something in the air that causes this. Something in air causes spoiling. The independent variable is the thing that he's changing. What is he changing between the two different trials of this experiment? Well, he's changing whether or not it's open to the air. So whether open or not. And the dependent variable is what responds to the independent variable. So we have one container that's open, one that's not, and we expect a difference in what? We expect a difference in growth or spoilage. So your independent variable causes your dependent variable, right? So being open causes more spoilage. That's our hypothesis, right? Constants are all the things that have to be the same between the two different groups that we have. So we had one that was open, one was not, but they both have the same broth. Boiled both of them, and with both of them we waited the same amount of time. And you could probably go on and on with all the things that you tried to keep the same between the two different setups. Your control group, and I like to add the word group because I think it helps, is contrasted with your experimental group, which I didn't put as a separate term. So we have two groups of flasks, the one we're experimenting on and the one that we're not experimenting on. Your control group doesn't get the change in the independent variable. So your control group is the one that's open to the air because it's being treated normally. Your experimental group is the closed container. That's the one that we're experimenting on. We're trying out closing the container to see what that does. So those are the different parts of the experiment. Having those constants and having a control group are what help make your experiment more valid. The other thing you have to do to encourage your experiment to have good results is repeat it multiple times so that you can evaluate the precision of the data. If we do this once, it could be a fluke, it could be an accident or a mistake, the results we get. If we do it 10 times, and 8 out of 10 times we see that the open container is the one that grows bacteria faster, that's going to be a pattern that we can trust and rely on. That's fairly precise data. However, if we do it 10 times and 5 times we get growth and 5 times we don't in our open container, that's more confusing and unsure and not precise enough for us to draw a conclusion. The parts of an experiment sometimes get confusing for students. Oftentimes when I ask students to tell me whether or not an experiment is valid, they'll try and throw in there that, oh yes, it's valid, it had an independent and a dependent variable. All experiments have those, whether they're valid or not. It's not an experiment unless you have one thing you think causes another. So just having an independent and dependent variable doesn't make it valid. However, having constants and a control group does help increase the validity of your experiment. Another concept that comes up in this unit is the concept of a black box. Remember what a black box is. Let me define it for you. A black box is anything that cannot be investigated directly. And you can think of lots of things that cannot be investigated directly. I apologize for my handwriting, especially on the iPad. Anything that cannot be investigated directly might be that way because of a lot of different reasons. For example, it's hard to investigate exactly what happens to the dinosaurs because it happened so long ago. We would have to be able to either go back in time or somehow pull up a recording of the ancient past, neither of which seems very likely. Other things might be too small for our eyes to actually see them, like atoms, or they might be too large for us to see them all at once, like the entire universe, or it could be too far away, like the sun. So a black box is anything that for some reason we can't just open it up, look inside, and go, aha, there's the answer. Most questions in science that are of any interest at all are black box questions. The experiment that I just had you look at in the previous frame is a good example of that. It's a black box, what's going on inside of that broth to cause it to spoil. We now have microscopes and we can see microorganisms and what's causing that. But in the time of Louis Pasteur, the man who did that experiment the first time, they couldn't see that. So he was investigating a black box. He had to infer, based on his observations, what must be going on inside of that flask. And that's really where the fun of science is, in investigating black boxes. Another thing that comes up in this unit, misconceptions. Things that people think are true but actually are not true because they haven't really thought it through 100%, right? They're not using logic and evidence, they're just jumping to conclusions. For example, a common misconception that students have, and that many people have, even after having taken a physics course, is this idea that heavy objects fall faster than lighter objects. It's not true. If I were to drop an apple, a safe, and a tennis ball all from the exact same height at the exact same time, they would hit the ground at the same moment if there were no air resistance, if they were not pushing back against the air, because obviously there's going to be more pushback against the safe. The apple and the tennis ball probably have almost the same air resistance. But the idea here is that it feels intuitively like heavy things should fall faster because we think of falling as being due to gravity, and it is. But, and here's the tricky part, even though falling is caused by gravity, so is not falling. If you think about it, your mass is what resists being moved. The more massive you are, the harder you are to move, and therefore the harder you have to be pushed or pulled. Gravity's doing the pushing and pulling, so it has to pull harder on the safe to make it move as fast as, say, that apple or that tennis ball. A lot of times what helps people understand this misconception better is to think of pushing these objects along a surface instead of letting them drop. If you hit them all with the same amount of force, the safe would not travel very far, the tennis ball would go flying, and the apple would be somewhere in between. which must mean that if you want them all to hit the other side of the room, hit the wall on the other side of the room at the same time, you're going to have to hit the safe harder. Well, gravity pulls harder on the safe than it does the apple or the tennis ball, and that's how all three objects can hit the ground at the same time. So this is a complicated misconception. Now, don't get confused. Remember, your quiz tomorrow is not going to be on which object falls fastest. That's not the point. The point is that misconceptions are very common, right? People think they understand scientific concepts when in fact they don't completely understand them. They're making assumptions and jumping to conclusions that aren't true. And finally, in this unit, we talked about SI units. SI stands for System International, or International System. And these are the units that are sort of agreed upon across most of the world so that scientists in different countries don't get confused talking about the same thing. So the SI unit of length is the meter. Of course, you can also break that down into centimeters and millimeters and kilometers. Mass, it's the kilogram. We often used grams of things instead of kilograms. Time is in seconds. We don't use electric current in this class. Temperature is actually Kelvin, but we didn't use the Kelvin scale because my thermometers are in Celsius, which is also widely used by scientists. And that's degrees C. We didn't talk about the amount of substance in moles. That's something you learn in chemistry. We don't work with light intensity. But volume is in liters or milliliters. And then the other one that comes up is density. Density for us was usually in grams per milliliter or grams per centimeter cubed. Remember that 1 milliliter is the same as a centimeter cubed, and that milliliters are already cubed, so you don't put a little 3 up there. So those are the SI units that we use this year in class, and pretty much that's it for the Nature of Science unit. See you guys in class. Oh, and my goodness, I almost forgot for the umpteenth millionth time. Here is a shout out for Biondi and Zev, whom I promised multiple times to shout out to. There you go, guys. Your one and only shout out.